Hello, Algebra 2. Welcome back. It should be Thursday for you. We're going to continue finishing the notes from section 1.3, all right? So, picking up where you left off. Hopefully this looks familiar, all right? This was from yesterday's video. We started talking about transformations, transformation rules, and also kind of like a little description of what's happening. So last time, if you remember, we talked about horizontal shift and vertical shift. We're going to talk about the rest of these today as well. So horizontal shift, if you have a parameter, something that's changing the function, all right? If you have your parameter on the inside of the function, so here it says f of x plus h or f of x minus h, those are going to correspond to horizontal shifts left and right respectively here, okay? The vertical shift, if you have f of x plus k, so here the plus k or the minus k, I'd like to think of it as it's on the outside of the function, it's changing the output. Again, here at the top with our horizontal shifts, we made changes to our input before we even applied the function. Here with our vertical shift, we apply the function first and then add our parameters on the outside. So if you have f of x plus k, you're shifting up k units. The graph is literally moving up. It's a vertical shift. Or if you have f of x minus k, you're shifting down k units. Again, down, negative, all right? So keep that in mind. We're going to talk about reflection, and we're going to see some examples of some stretches and compressions, vertically and horizontally. So my first one, if you look at this one right here, g of x equals f of negative x. Again, looking at this transformation rule, I can already use that to go look. So if I want to take that rule, g of x equals f of negative x, and if I go back one slide, f of negative x, you can look for right here, boom. Okay, so now I'm looking at this rule, f of negative x should be a reflection across the y-axis. So my graph should be reflecting, all right, according to that rule. Let's see if that's actually true. So again, this is the original problem that I had from yesterday, f of x equals 3x. We got that table of values. You input any number into that function, and I just multiply it by 3, all right? So 0 times 3 is 0. 1 times 3 is 3. 2 times 3 is 6. You get the idea. Now I'm writing another transformation rule. So this function g, again, it's a new function that I'm going to define as f of negative x. So you have a whole bunch of inputs, whatever they may be, negative 10, negative 5,000, okay? So you've got inputs, sense the parameter, and you can think about it, negative x is equal to negative 1 times x. I mean, it's the same thing, right? So if your parameter here is a negative 1, I'm multiplying by a negative 1 on the inside. Don't worry too much if that doesn't make any sense right now, but just know that I am making a change to my x, and then I'm applying the function, all right? This negative on the inside, that parameter, it's on the inside of the function. It's in between these parentheses. I'm making a change on my input before I even apply the function. So what would that look like? Here's my original inputs. I need to change the input to be negative x. So now everything just turns to the opposite of itself. So 1 becomes negative 1, 2 becomes negative 2, 3 becomes negative 3, and so on. Negative 15 would become positive 15. Again, just taking the opposite of it. And then g of x says, all right, awesome. You took negative x, you made all of your inputs negative. Now, just apply the function to these new inputs. Again, my original function was multiply everything by 3. So, I'm going to take these new inputs, now that I've made everything negative, I'm just going to multiply everything by 3. So, 0 times 3, still 0. Negative 1 times 3, negative 3. All right, negative 2 times 3 is negative 6. Negative 3 times 3 is negative 9. What do we got? Negative 12. 3 times 15 is 45, all right? Again, you can add whatever inputs here. You just got to follow that function rule. So again, since the change is happening on the inside of my function, I need to change the inputs here and then apply the function based on these like new inputs, all right? Pause if you need to. We're going to take a look at this. So what we said, that was the algebra that was going on behind it. What we said was this should be a reflection across the y-axis. Y-axis. So here I am at Desmos. I have this blue line graphed, f of x equals 3x. Let me make sure this is it's in projector view. Okay, so f of x equals 3x. Here's that. My transformation that I wanted to do was g of x equals f of negative x. So right here, g of x equals f of negative x. I'm going to turn that transformation on and see what we see. Anyway, we're going to see what happens. So turning that on, it should be a reflection, so it should look something like this. Boom, there it is. Everything got reflected across the y-axis. So think about this is like your line of reflection. Everything just flipped across that line, all right? So again, whatever that may be, so I'm going to say, what if I let that function be x cubed? So if I type in x cubed, all right, the blue line is my original function. So this is the graph of x cubed in blue. With that transformation turned on, g of x equals f of negative x, I see now a reflection across the y-axis, all right? So it holds true for any function. Okay, let's go back to the PowerPoint. Oh, there it is. Okay, so what about f of x squared? Now I'm changing the original function. We're just going to look at a different example. F of x equals x squared. You take all of your inputs and you square them. So 0, 0 times 0 is 0. 1, 1 times 1 is 1. 2, 2 squared, or 2 times 2 is 4. 3 squared, or 3 times 3 is 9. All right, 4 squared is 16. So what if I said my new function rule is g of x, I'm defining this new function to be 3 times f of x. So 3 times f of x, let's go look and see what that would be as a description of a transformation. So again, my function rule is g of x equals 3 times f of x. Here's that little rule sheet. If I have 3 times my function, I have a parameter times my function. So that looks like here, a times f of x, a times f of x. So it's going to be a vertical stretch or compression. If I take a number, if I take a parameter, and I multiply it on the outside of my function, like we have 3 times f of x, it's going to be a vertical stretch or compression. So which one? So again, if you're looking at that PowerPoint, here I say a times f of x. When a is greater than 1, and yeah, indeed, 3 is greater than 1, it is going to be a stretch vertically by a factor of a. So it's looking like we're going to have a vertical stretch because that parameter that we're multiplying by is greater than 1. On the other hand, if a times f of x, if a is greater than 0 but less than 1, so like 1/2, 1/3, 0.212, those are between 0 and 1. If you have a parameter that's a small number between 0 and 1, then you're going to be compressing vertically, all right? So let's take this fact that it should be a vertical stretch and go back to here. So g of x equals 3 times f of x. Again, my little g of x rule, he says, first, I want you to apply the function as we did here. We've got the inputs. We've applied the function by squaring all of our inputs. And then g of x says, take that function and multiply everything by 3. So now, I'm going to take these outputs from my original function, my f of x values, and I'm just going to multiply them by 3. So take this entire column, f of x, multiply it by 3. So 0 times 3, still 0, super exciting. 1 times 3, 3, 4 times 3, 12, 9 times 3, 27, 16 times 3, 48. Did I do that math in my head correctly? Yes. All right. So, and again, if we think about this, it should be a vertical stretch. So all of our output values just got multiplied by 3. They got a lot bigger. Things should start stretching. Let's look at it visually, all right? Oh, I'm going to need to go put in x squared. So let me change that to x squared real quick. So the function that I'm going to graph now is x to the power of 2, x squared. That is just a regular parabola. All right, and then the function, or excuse me, the transformation rule that we want to use is g of x equals 3 times f of x. So here I'm going to go turn on this transformation and make sure that my parameter a is set to 3, and I should see something start to stretch. So g of x equals, oh, that's because it's, so here is, give me just a second. All right, so there's our original equation. They're lined up the same. It's just x squared. But as soon as I make that parameter, if I increase it to be 3, you see how it's stretching? Now everything's getting a little bit skinnier. So there, in the dashed red line, is my g of x function graphed. Again, my original was blue, all right? And with the vertical stretch, everything just kind of got stretched out, so it got a little bit skinnier, all right? That's what a vertical stretch would look like. What would a vertical compression look like? Let's say we had g of x equals 1/2 times f of x. Again, that is our parameter. It's between 0 and 1, so that would be a vertical compression. So let's make it 1/2. Okay, so there's the original function. Now we're starting that compression, the vertical compression. And right there is 1/2, all right? So again, the original is in blue. After that compression, your new transformed function is in the red. It's a little bit fatter, all right? It got compressed a little bit, squeezed down. So again, stretch and compression, that was vertical stretch and compression. Okay, there's my mouse. So next thing I want to do is just be able to write some transformations here, all right? Let me get a red and blue. So the blue is the original function. It's probably small for you here. You can read it on the PowerPoint as well. It says G, the red G here, so this red one is a transformation of f. All right, so I've got g of x, I have f of x. It says the graph below shows f as a solid blue line and g as a dotted red line. We see that. And it's asking for what's the formula, what is this transformation rule of g in terms of f. So I don't know what f of x is. It could be x equals negative, or excuse me, it could be f of x equals negative x cubed plus 3x squared. It could be anything, right? But if we had to write g of x in terms of f of x, what's happening to our transformation? My original is this blue. Again, to get from the blue line to the red line, it looks like everything just shifted up. And it shifted up how many units? Well, if I just pick a point, I'm going to pick this point right here. Okay? To get from that point to this point, all right, both when x equals 3, again, to get from here to here, I just went up 1 unit. So g of x, the red line, took f of x and just added 1 to it. It did a vertical shift up 1 unit, all right? We're going to do a couple examples of these, so don't get too worried if this isn't making sense yet. Again, here I'm seeing they look pretty much the same. It's just a shift. So g of x equals my original function plus 1. Okay. Oh, and then that was it if we need to go back and review it. So what about this? G is a transformation of f. It's the same thing. My original function is f of x in blue. G of x is the transformation rule that I want to write. So what's happening with these guys? All right, I'm looking here. Notice how if I look at these kind of depths, so the minimum here and the minimum here, and the maximum here and the maximum here, the height of those minimums and maximums, this height right here, didn't change. So I know it's not any vertical stretch or compression. The height didn't change, but it looks like it kind of got squeezed in. So it looks kind of like a horizontal compression, all right? Again, to get from the blue to the red, it looks like I took the blue and I just kind of squeezed it this way, horizontal compression. So how would we write that? Horizontal compressions, if you look back here, I'm gonna flip it over to, okay, just look down here. Horizontal compress. Compress horizontally, I have f of a times x, where a is greater than 1. So I'm looking for a transformation rule that looks like this. G of x equals f times something, or excuse me, f of something times x. And I have to figure out what that something is. So let's go look at the board here. So I'm just going to try and pick a point. And I'm going to pick this point right here because it looks nice and even. Actually, I'll do that in blue so we don't get that mixed up. All right, so I've got that blue dot here where x equals 6. Looks like that's the maximum. The corresponding maximum in the red is this dot here. So what exactly happened? I went from 6 now to 3. I went from 6 to 3. I cut it in half, right? So I compressed it by a factor of 2. Everything got compressed down by a factor of 2. Again, going from 6 to 3, everything got compressed by a factor of 2, all right? So I could say that my transformation rule is g of x equals f of 2x. I think I got maybe two more. Okay, looking at this one thing I noticed right off the bat is the shape hasn't changed, all right? The shape hasn't changed, looks the same, doesn't look like any stretches or compressions vertically or horizontally. Maybe it's just a shift. So again, here's my blue function. I don't know what the exact equation of it is, but we're just gonna call it f of x. How do I get from f of x, the blue, to g of x, the red? Again, let's just pick a point. I'm gonna pick an easy one. You know, make it easy on yourself. Pick the minimum. Check it out, this minimum right here. The corresponding minimum in the red is over here. So how did I get from that minimum to the blue minimum to the red minimum? Wow, that's annoying. So to get from here, all I did was shift it over 1, 2 units. So it looks like, so far, a horizontal shift to the left 2 units. So what would that look like? I can go back to my rule sheet and I'm not going to switch it over. But again, this is a printout of it. You can look at the PowerPoint. A horizontal shift to the left means that I would have x plus something, all right? And that plus something is how many units? We said that we're moving 2 units. So I'm going to say f of x plus 2. All right? So that was that one. Before I erase, I want to point out that since I moved to the left, this is kind of weird because it's opposite. If I move to the left, which is the negative direction of x, I said plus 2. So it's opposite. And if you look at that rule sheet, let's say that I moved to the right, which is in the positive direction of x. If I made a horizontal shift to the right, my rule would be negative, all right? So it's kind of backwards there. But again, here, since I'm moving to the left in the negative direction of x, I'm going to write f of x plus 2. It's kind of backwards thinking that way. All right. Last one here. Let me erase those points. You guys are doing good. Hang in there with me. So this last one, again, looking at that shape, the shape is definitely not the same. There's some sort of stretch or compression involved here, right? So it's definitely not a shift, but it is some sort of stretch. Let's look at, I'm just going to pick a point again. I'm going to make it easy on myself, and let's just use this one, the maximum. Let's use that point here. So I've got that maximum on my blue on the original function. We have a maximum at 2. In my transformed function, my maximum here is at 1. All right, so how do I get from 2 to 1? I just have to divide by 2 or multiply by 1/2. So g of x took my original function, again, it's looking like it's going to be a vertical compression, all right? So it took a vertical compression by a factor of 1/2. All right, so again, just looking at those, being able to recognize what's changing, what's stretching or compressing, what's shifting, and try and see if you can write some function rules for this. So I'm going to say come back to meet me, because I think that was all I have. Come back to meet me in, no, I got more, hang on. Actually, you know what, we're going to talk about this in the classroom, okay? So finish up notes. All right, we're done, yeah. Don't look at that, we're done. Go to Blackman 107, come see me, come show me your notes. We'll go over some review questions. We're done, so come see me about 30 minutes into class.